This is lecture 3I for Calculus 1 on the derivative of logarithms. We wait until this point in the chapter to take the derivative of logarithms because we need to use the use implicit differentiation, and then we also need to use the chain rule. Okay, so what we're trying to take the derivative of is y equals log to the base b of x. The first thing we do is recall that exponentiation is the inverse of logarithms. So I'm going to raise everything by the power b. So y becomes b to the y. On the other hand, if I raise log to the base b of x as the exponent of the base b, this b and the log b are inverses of each other, and I just get x. And so now I have the term, equation I'm going to work with. X equals b to the y. Previously, we had y isolated here, the dependent variable isolated, and we are looking for dy by dx, but we have seemingly complicated the situation by now bearing y up there in the exponent. We need to use implicit differentiation. So to do that, we apply the derivative operator to both sides of the equation. Here, d by dx of x itself is just 1, so that's done. Over here, we're taking d by dx of b to the y being some function of x. The outside function here is b to the exponent, and the inside function is y. In terms of f and g, b to the x would be f, and y would be g. So first, I take the derivative of f, derivative of b to the x, and evaluate it at y. So here is the term for taking the derivative of the outside function. Then I need to take the derivative of the inside function, and I write dy by dx because I don't even know what else to do with it. I can't evaluate y. I do know it's a function of x, so I have to include it. Now I solve for dy by dx and get the answer I want. So dy by dx equals 1 over b to the y times the natural log of b. No problem dividing because logarithms are never 0, or exponents are never 0. Okay, but what is b to the y? It's just x. So I can replace b to the y with x, and here is the answer. So when I take the derivative of y equals log b to the x, the answer is 1 over x times the natural log of the base. Here's the rule stated without that intervening step. Of course, if we have the base e, natural log of b is 1, and we have an especially simple simple result. The derivative of log x is 1 over x. Often these logarithms appear with a complicated argument, and then you have to use the chain rule. Right, let's use this situation first. I'm going to take the derivative of the natural log, and the argument of the log will be some function u of x. Remember that a log is a function, everything after it is its argument, not a multiplier, its argument. So the argument of log is u of x. This actually could have been in parentheses. The derivative is 1 over the argument. That's right here. Now I have to take the derivative of the inside function, du by dx. If we're using an arbitrary base, we're taking the derivative of log to the base b, and the argument is some u of x. The derivative of the outside function is 1 over u of x times the natural log of that base. Then you have to take the derivative of the inside function, this unspecified u, so you have to multiply by du by dx. If I want to take the derivative of log to the base 4 of x, the answer is 1 over x times the natural log of 4. In the second example, I'm going to take the derivative of log x. In standard notation, when there is no base specified, log refers to base 10. I want to point out that in calculators and in some of these online graphing programs or some program that you might buy, this convention is not always held. I've seen cases where log 10 means log to the base 10, and log is used as ln. So what you have to do is, when you're using one of these programs or one of these calculators, find the list of available functions and look down there till you can find out what they really call log and ln. So taking the derivative of something, of log to the base 10 of x, it's 1 over x times the natural log of 10. Now I want to take the derivative of the natural log composed with sine x. So sine x is the argument of the natural log. This is its argument right here. So the outside function is natural log, the inside function is sine x. I take the derivative of the outside function and get 1 over the sine of x. Then I have to take the derivative of the sine of x and get the cosine x. And here's your answer. In the last example, I'll take the log to the base 10 of this polynomial. The outside function is log to the base 10. The inside function is the polynomial 12x squared plus 6x. I take the derivative of the outside function, and that gives me, here's the argument. So I get 1 over the argument, and then the scaling factor, natural log of 10 here. Then I have to take the derivative of the inside function, and here's the answer. One real benefit of this logarithmic differentiation is to simplify complicated rational functions, or even just any complicated function. The idea is that you take the logarithm of both sides, but the logarithm you want to use is ln, natural logs, because you don't have that extra scaling factor in there. It's simpler. Then you try to make use of the rules of logarithms, which are summarized here. Okay, the log of two terms multiplied together equals the log of the first term plus the log of the second term. When you're taking the log of two terms that are divided, this breaks out as subtraction. Now, if you take the log of any term raised to the power, say x, the exponent comes out in front. The entire exponent comes out in front. I'm sure you're familiar with those. You use implicit differentiation, and then you carry out the result using chain rule and product rules, and then solve for the derivative. So for example, we're going to take this complicated expression, y equals the square root of x times e raised to the x squared times x squared plus 1 all raised to the 5th power. And what we want is dy by dx. So first take ln, take the natural log of both sides. So you have the natural log of y on this side and the natural log of all this on the other side. Now you can use the law of logarithms to break out all the terms that are multiplied. So this breaks out as a log of the square root of x. Then you have the log of ex squared. Then you have the natural log of the last term. Now look back through it, and if there are any exponents, put those out in front. Square root of x is really x to the 1/2, so the 1/2 can come out in front, leaving natural log of x. A very simple result. If I have the natural log of e to the x squared comes out in front, but natural log of e is 1, so I'm done with that. Here, the 5 comes out in front, and now this is an opportunity to make an unforgivable error. If I have the natural log of two terms added together, those do not break out as addition, only if they were multiplied together. So now we're done with the laws of logarithms. We can try to take the derivatives.